after we got done with class today, I thought of three things that I should have mentioned that I forgot about. One is we're going to talk about quite a bit in imaging, that's blooming of the space charge. But since we're in the internal components of the X-ray tube, these two are very applicable. So we're going to start with off-focus radiation, then we'll work our way back up. So off-focus radiation, as described by Bouchon, is radiation that occurs anywhere aside from the focal tract, right? So the focal tract is the area of bombardment for the electrons. So we have our filament, and we send the electrons across the tube to interact on the focal tract, right? So the focal tract is the actual area of bombardment. We call the whole disc the target. The focal tract is really, truly the target where we plan to hit the anode with the electrons. So keep in mind what we've got are a lot of electrons, and whenever we hit it with KVP, the electrons travel across the tube at extremely high rate of speed. So they travel across the tube anywhere from 1/3 to half the speed of light. So they're traveling very, very fast. And even though they're tiny, almost to the point of non-existence, they're still matter. So anytime you throw matter hard enough, there's the probability or the likelihood that it could bounce. So let's say we've got an electron that travels across the tube at any rate of speed, and it hits hard enough that it doesn't just slow down. What it does is it hits something solid enough that makes it reverse its course, and it bounces backwards. But inside the tube, you've still got a relative positive charge over here, very high positive charge or really high negative charge on the cathode end, high charge, positive charge on the anode end. So these electrons, if they bounce off, they're still going to be attracted to the positive charge of the anode end of the X-ray tube. So if they bounce off, they're not going to travel too far towards cathode end. So they're still going to be attracted. So they made a U-turn, and they're going to make another U-turn, and they're going to come back, and if they have enough energy, kinetic energy left, they still can create an X-ray photon. Now, if our focal tract is right there, and that's the only thing that we consider our focal tract, and that the size of that focal tract, because of the line focus principle, it is what gives us a sharpness of recorded detail. An X-ray photon that makes this U-turn, that hits anywhere off of that focal tract and creates an X-ray photon, then becomes off-focus radiation. It's off-focus radiation because it was created somewhere aside from the focal tract. Off of the focal tract, off-focus radiation. And it occurs because X-rays, or the electron bounced and it hit somewhere aside from the focal tract and created an X-ray photon off of the focal tract, off-focus radiation. So that could occur anywhere on the target. And I think in the diagram in the Bouchon book, it shows where the screw or the bolt is going through the anode into the stem. So it can happen anywhere. Off-focus radiation, you're going to have a tendency to equate to scatter radiation. It's not the same thing. Scatter radiation is secondary radiation that comes through the patient. Off-focus radiation is primary radiation because it has not interacted with the patient yet, but it's created somewhere aside from where we want it to be created. So that's off-focus radiation is primary radiation created off of the focal tract. The problem with off-focus radiation is, let's just take this one photon that we created here. If this controls our sharpness of recorded detail, creating another X-ray photon up there decreases our sharpness of recorded detail. So off-focus radiation reduces sharpness of recorded detail. Spatial resolution suffers from off-focus radiation. What we're going to learn later on is that our collimator housing helps to take care of that. We have two sets of collimators. The first set of collimators are specifically designed to help with off-focus radiation. So that's off-focus radiation. Off-focus radiation, bouncing electrons. Now the other two are also going to give us technically off-focus radiation, but we're not going to call it off-focus radiation. And they're kind of similar, or they're a lot similar, caused by different things. All right, so we talked about the focusing cup. You got the focusing cup. It's negatively charged to compress the electrons that are bowled off of the filament, so that whenever they travel across the tube, they don't spread out and they interact where we want them to interact on the focal track. Right, so if we don't have that negative charge, then our electrons can spread out and interact on the target aside from where we want them to interact. Again, reducing the sharpness of recorded detail. Now here you're going to have a tendency to say, well, if this is a focal track and they're interacting out here, that's off-focus radiation. I 100% would agree with you, but we're not going to call it off-focus radiation. In this case, if the focusing cup loses its negative charge, you're going to get all that off-focus radiation. You're going to get a loss of sharpness for recorded detail, but we're going to say that that's just loss of recorded detail because we've got a failure of the focusing cup. Splitting hairs. It's off-focus radiation, but we're going to reserve that term for those bouncing electrons. So yes, that's off-focus radiation, true, but we're not going to call it that. We're just going to call it enlargement of the focal spot size because of the loss of the function of the focusing cup. All right? So the third thing we've got then, after focusing cup failure, is blooming of the space charge. And that occurs even if our focusing cup is doing its job. So we got a negative charge on the focusing cup, negative charge on the focusing cup. But let's say you use an MA station that is maybe a 1200 MA station. Even on a large filament, you're going to have a hard time compressing that cloud of electrons enough to where once you hit the tube with a KVP, they don't spread out a little bit. Okay, so blooming of the space charge refers to an enlargement of the space charge to the point that the focusing cup can't compress it enough to put it onto the anode where we want the stream of electrons to interact. So is that off-focus radiation? Yeah, it's off-focus radiation, but we're still not going to call it off-focus radiation. We're going to reserve that for those bouncing electrons, but that's still off-focus radiation. The result is the same. We get a larger impact, which is going to give us loss of sharpness recorded detail. So the two things that are going to cause blooming, by definition, focusing cup failure will cause blooming, but we're not going to say that in this case. Specifically, what we're going to call blooming, causes for blooming, are high MA stations and long prep times. So a different reason not to use long prep times would be because you stack so many electrons on your filament that the focusing cup has a difficult time compressing them enough. And so when the KVP comes into play, they spread out and interact on the target in a larger area than what you wanted them to be interacting. So you lose sharpness or recorded detail. All right, so hopefully I've explained that well enough that you can kind of keep the three separated. Off-focus radiation. Radiation is created by electrons that hit the anode, they bounce, but then they return to the anode and create X-rays somewhere off of the focus, off-focus radiation. Focusing cup failure leads to a spreading of the stream of electrons before they interact with the anode, and you do create some X-rays off of the focus itself, and lose sharpness or recorded detail. And blooming occurs even if the focusing cup is functional. Blooming occurs because you use very high MA or long prep times, and you overpopulated essentially your electron cloud, so that when you hit it with a KVP, they spread out, interacted on the target in a larger area. All three cases, you lose sharpness or recorded detail. Lower MA, no short prep times, combats that. You can't really do anything about that. That's a type of tube failure. really not related to heat. And then off-focus radiation, you can't do a whole lot about that in its creation, but you can do something about it in its emission from the collimator housing. We'll talk about that later on. So hopefully that's all.